All right, well, I'll get started. We begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and your creation. Just help us to understand a little bit more today about capacitors, Lord. In your name I pray, Lord Jesus. Amen. Okay, so first of all, I don't know how to take my own advice. I have warned you at length in class that, you know, if the charge distribution is infinite, there's no guarantee that we can make the voltage zero at infinity. And indeed, that's true. So if you try to, for problem 2 in the mission, I say make the voltage zero at infinity, R equal to infinity, and you can't do it. I think it almost has to be minus infinity. So ignore that, all right? Okay, so capacitors. And we've talked so far, capacitors. We talked about how to calculate the capacitance for particular physical capacitors formed by either a parallel plate or like a cylindrical shell or a spherical shell, right? And we found the formulas for capacitance for each of those 3 geometries. Of course, I think parallel plate is more often than not what people think of when you think of a capacitor. But fundamentally, capacitance is defined to be what? It's Q over V, right? So this is the capacitance, essentially the definition of capacitance for a circuit element. You've got charge Q and minus Q on the plates of the capacitor, whatever those are, and you have a voltage V difference between the plates. That defines the capacitance of that object. All right, so now we want to talk about the concept of equivalent capacitance. And so the concept of equivalent capacitance is basically the fact that we can take several capacitors arranged in particular geometries, and we can think about them instead as a single capacitor in its place. All right, so so let's start out with example 1, which is series. So things are in series means that if there's a current flowing through the one object, it has to also flow through the other object. You might say, what's current? And the answer is you have to wait till later, maybe next class. I'll tell you. So I guess I can spoil the news now, though. The current is the charge per time that flows through a particular wire, let's say. So here, if this is C1, all right, and this is C2. So our symbols here, these symbols that's our symbol for a capacitor, all right? And in this kind of picture, the other lines are understood to be wires, all right? And they're ideal wires, so they don't, they're perfect conductors, you could say. Okay, so here's the thing. If we have charge Q, let me use some color. We have charge Q here. We'd have charge minus Q over here. We'd have charge Q here. And we'd have charge minus Q here. And I could start by saying Q1 and Q1 and Q2 and Q2 just to distinguish logically. But the thing is, because they're in series like that, right, the only way that the charge can get to the middle branch is if it flows either from one of the plates. Basically, the charge in here is coming from, you know, this wire and these plates. You could think of it that way. So what that means is that Q1 has to be equal to Q2. All right? Because there's no net charge here, so that whatever's negative goes here, it has to be positive there. There has to be a net charge of 0 on the wire there. So that you know, we can justifiably say we've got Q and minus Q there. And so this is, excuse me, sorry, I am apparently sick. Anyway, so long story short, we have the same charge on all of the plates, either plus or minus, all right? Because if you just think through it, it has to be the same charge, otherwise. So it has to be the same charge. Now, let's see here. So then the question is, what goes on? So we've got, let's go with it. So we got C1 is equal to what? Q1, right? Over V1. And we have C2 is equal to Q2 over V2, where I'm defining, you know, the change in voltage. Maybe I should say change in voltage 1, change in voltage 2. I kind of like that more. Let me do that. So change in voltage 1, change in voltage 2. All right. And let me just introduce some extra letters here to try to confuse you more. I mean, I'm not trying to confuse you, but if it happens, it happens. All right, so here's A, and I'll put B up here because I think that's what I have in my notes. And just to give, and just to be weird, I'm going to call the point in the middle. Oh, I don't want to call it C. Tell you what, I'm going to call it Pac-Man. There we go. Okay, great. So my point to you is simply this. The change in voltage 1 is going to be equal to the voltage at B minus the voltage at Pac-Man. And the voltage dropped, the change in voltage across capacitor 2 is going to be the voltage at Pac-Man minus the voltage at A. That's the difference in absolute voltage measured at those three nodes. All right? So, all right, great. Now, the idea of equivalent capacitance, all right, is that you can imagine taking all of this, right? You can take all of this, and let me redraw it again so it's not so busy. But basically the idea is this. You've got, you know, you got these two capacitors in series, like so, all right? And basically you want to just think about putting a black box around it, all right? So that you've got, you know, B here and A here, and just replacing it for all intents and purposes with the so-called equivalent capacitance over here. I'll just say EQ. All right? That's the idea, is like, it doesn't really matter the details. The claim is that there's an equivalent capacitance that we can replace this more complicated circuit with. All right? Okay, so then what is, well, let's work it out. So the basic idea here is that VB minus VA is equal to what? So VB minus VA we can rewrite as VB minus VPacman plus VPacman minus VA. Oops. In other words, maybe you guys would find it more natural. We're saying it's the change in voltage 1, excuse me, the change in voltage 1 plus the change in voltage 2 is the change in voltage from A to B. I hope that makes sense.
Do you have an equal sign?
This is a parenthetical comment, so yeah, sorry. I'm not trying to multiply there. Let me put a dividing something or other. There. I don't use that one too much. All right, so look, you can solve this. What is this equal to? So check it out. Change in voltage 1 is what? C1 Q1, right? Change in voltage 2 is C2 Q2. Right? But remember, Q1 is equal to Q2. So I really just have C1Q and C2Q. And so I put that up here. I have C1Q plus C2Q. Right? And I can factor the Q out. So I got C1 plus C2 times Q. All right. So let's solve for Q over VB minus VA, what do we get? Looks like we get 1 over C1 plus C2, right? Uh-oh. Have I done something wrong? Just a second. I don't trust myself. I'm sick. I did really stupid stuff yesterday, like really stupid stuff, so watch out. Do 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 do. I think that's right. Now this is supposed to be equal to what? Have I? Yeah, well that's the thing, is it wouldn't be 1 over CQ, it would just be 1 over, it would be CQ, you know?
Yeah.
Which is not correct, because it's dimension, like I can't just say that this is equal to CQ, right? That would be nonsensical, because what I would have is like the units on that equation would be 1 over farads on the left-hand side, but farads on the right-hand side, right? So I've made a mistake. Where is it?
Changing the voltage for 1 and 2, the C1.
Thank you, perfect. This is the garbage in that's made the garbage out. So let's fix this. This is wrong, and all right, great. So right here, this was the mistakes right here. Let's, thank you, perfect. So yes, I should actually do the algebra. So this says that, and if you'll allow me this short Manga style calculation, we've got like change in voltage 1 is equal to what? Q1 over C1. There we go. If you saw this like 5 minutes ago and you didn't tell me, you're a bad person. Let's see here. You know who you are, Kirk. Let's see here. No. Yeah. You see it?
No comment.
Let's see here. So it's this. And of course we can erase the 1 and the 2. And then plug that in over here. So we've got Q over C1 plus Q over C2. Factor the Q out. And then this gives us 1 over C1 plus 1 over C2, which is ever so much more lovely, because at least it has units of farads, right? 1 over a farad is a farad. So it's dimensionally not insane. You know, we don't like equations that are like seconds is equal 1 over seconds. That's not a good equation. But this we identify as the equivalent capacitance. And so here you go. That's the takeaway message of all this, is that the equivalent capacitance of a series is the sum of the reciprocals reciprocated. There's another way you could write this formula, right? If you multiply that equation by C1, C2, what do you get? Yeah, exactly. C1, C2 over C1 plus C2 is how that goes for 2 capacitors at least. All right, so that's that. So next up, we can talk about, all right, so that's, I guess it's not really an example, it's more of a theorem. I'm going to erase this example. I'm raising this example to a theorem. We don't do many theorems in here, but this is a theorem on series capacitors. Now an example. All right, so suppose you've got 10 microfarads in series with, I don't know, let's say 6 microfarads. There we go. Right? So this is equivalent to just 1 capacitor, right? With CEQ equals to 3.75. So you have 10 microfarads times 6 microfarads divided by 10 microfarads plus 6 microfarads. You start to realize writing so many microfarads was dumb, and you realize that you could have just written 60 over 16 and kept one of the microfarads, because that's how it works out. And then somebody tells you that that's 3.75, and you're inclined to believe them. So there you go. Let's do a little bit more with this example, all right? Let's do a little bit more. Suppose in addition that there's, I don't know, 37.5 volts. Oh, maybe I don't do 37.5. Let me think for a second. Well, let's just suppose that you've got, you know, this is connected to a battery. And we'll make it a 9-volt battery, because you've heard of those, right? So my question is, if that's a 9-volt battery that's been attached, right, and it's charged, my question is simply this: what's the charge on the 10 microfarad capacitor? What's the charge on the 6 microfarad capacitor? And what's the voltage dropped on each capacitor? All right? So let's figure that out. So to start with, I say, okay, so we have C equivalent, right, is equal to what? It's equal to Q divided by, well, apparently 9 volts, right? So that tells me that the charge on the capacitors are 9 volts times 3.75 microfarads. What's that give us? What's 9 times 3.75? 33.75? Okay, I'll believe it. 33.75, and that would be microcoulombs. All right? So this is a series capacitor. I'm missing words today. It's a series arrangement of capacitors, right? So the charge is the same on both of them. So that is it. There's 33.7 microcoulombs on the 10, and there's 33.7 I lost a 5, didn't I? You guys told me 5, didn't you? Sorry about that. 33.75 microcoulombs on the 6. They have the same charge as we were just talking about, all right? But they don't have the same voltage. See? So the voltage on the 6-volt one, right, on the 6, let's call it V6, is equal. So, by the way, something that I've already shown you the dangers of not being clear on in your mind about is it's probably just a good idea to write these all down. So we've got C is equal to Q over V, right? So this also means that V is equal to Q over C. And it also means that Q is equal to CV. Each one of these has a place, all right? So you want to know all 3 of those just off the top of your head, really. So to find voltage, I take Q, and I divide by 6 microfarads. So in other words, I get 33.75 microcoulombs divided by 6 microfarads. The micros cancel. What do we got? 5.625, and this is volts. So there you go. That's the voltage across the 6 microfarad, all right? And then what's the voltage across the 10 microfarad? 3.375. How did you calculate that? You're cheating. All right, very good. So 33, we don't know that yet. We sort of don't know that yet, but you're right. And so somebody do the calculator for me. Well, anyway, like you said, it's going to be 3.775, yeah? If I can do my math. Is that what you guys got?
3.3.
Oh, 375? I can't do math today. It's not a good sign. Now, if we did that right, the sum of those voltage drops must be 9 volts. All right? Essentially because of this algebra right here. It's always this algebra. The sum of the voltage drops must be the net voltage drop between 2 points. All right? It's like the voltage equivalent of saying that, you know, you can break a journey up into a series of steps. One step after the other, you know. Okay, so anyway. Any questions? We good? I hope. Right. Next theorem. The next theorem, get rid of that unpleasantness. It's the theorem parallel. Or, as I will just usually say, parallel capacitors. So here, we have this kind of situation. All right? So again, I'm going to call the upper node B and the lower node A. And we're going to say we've got charge 1 here and we've got charge 2 here. So these capacitors are said to be in parallel. What that means, essentially by definition, is that they are physically connected to the same node on one side of their terminals, and then they're also connected at the same node on the other side of their terminal. In other words, they're coterminal. This also means that the same voltage must be dropped across both objects, right? So in parallel, we have that the voltage, the change in voltage for 1 is equal to the change in voltage on 2, which, by the way, is also equal to VB minus VA, right? Those are all the same voltage drop. Now, this time, I don't know. In fact, it's not true that they have the same charge, right? The charge on 1 and the charge on 2, they can be different. All right? So we'll just call them Q1 and Q2. So Q1 on this guy, Q2 on that guy. And of course, that means that there's also a minus Q1 down here and a minus Q2 down there, right? Fine. But so let's see here. My equation was what? So I've got Q1 over C1 equals to Q2 over C2 is equal to, well, anyway, that's the equality here, right? So, like, if you want to think about this, this would be equivalent to what? A single capacitor, and I can just maybe put the picture down here. This is equivalent to a single capacitor like this, right? Where we have Q equals to Q1 plus Q2 on that plate, right? Like the net charge on this capacitor would be the sum of the charges, right? If you've got charge Q on this plate, charge Q on that plate, the net charge on the plate of it, thinking of it just as one thing, would be the sum of the charges, right? So this should be equal to Q1 plus Q2 divided by the equivalent capacitance we're trying to figure out. So what can we do? Hopefully I don't murder the algebra this time. Help me out, guys. I could say this, right? Q1C2 is equal to Q2C1. I could say that.
Express the individual capacitances in terms of their
Second, I just lost you.
If you do like C1 is Q1 over VB minus VA, C2 is Q2 over VB minus VA, then you can put Q1 and Q2 in terms of the individual capacitances and the voltage drop, and then all that voltage drop should cancel when you have CQ equal to Q1 plus Q2 over the total voltage.
Ah! I lost you.
I think.
Just a second. All right. Yeah. All right, so so if I just take the reciprocal of this equation, I get CEQ over Q1 plus Q2 is equal to C2 over Q1 is equal to, it's also equal to C1 over, I'm sorry, those are both 2's. So CEQ is equal to C1 over Q1 times Q1 plus Q2, which is equal to C1 plus C1 Q2 over Q1. I don't really care about the charges here, right? So like you could take this equation here and solve it for Q2 over Q1, what do you get? So whatever Kirk said a minute ago is probably an easier way of deriving it. I'm just stuck with the algebra I have on the board here, guys. So Q2 over Q1 is C2 over C1. If I did the algebra right. Yeah, so this I can swap out for C1 times C2 over C1. C1's canceled. And we get C1 plus C2. You guys are like, I already knew that. Yeah, I know you guys already know it. But I want to show you how we derive it. Okay, so we derive it from the voltage being the same on both capacitors and the net charge on the capacitor being the sum of the charges on the individual capacitor. So these considerations are important when you're trying to do analysis and understand like how much charge there is on both capacitors separately, right? When we actually put numbers in and junk. So anyway, the net result here is that the equivalent capacitance is simply the sum of the capacitances. Yay. All right. So let's do an example, if I dare. So like, is what I have on the board a minimal path towards that formula? By no means. This is evidence that I'm sick. All right, that's what that is. So, so example 2 here. Let's suppose that we have. I'll put 10 microfarads here, and just to make it fun, 10 microfarads there. All right? And we'll put between nodes A and B, we'll say that VB minus VA is given to be, what do you guys want to put? What voltage do you want? It's your chance. What? 50. I heard a 50. I like a 50. I'll take that 50 volts. I'll take it. So then my question is, what's the voltage across each capacitor? And what's the charge on each capacitor? What's the voltage across each capacitor? 50 volts. Very good. Would I ask a question that dumb on the test? Yes, I would. Because I try to give gifts sometimes, but they're not always freely given. So it does give me information when I ask a question like that. It shows me the difference between the lost and the truly lost. But none of you will be truly lost, right? Because you guys all have potential now, so it's good. I'm sorry. I know, I regret nothing. I regret nothing. So the equivalent capacitance, right, is 20 microfarads. And so the total charge, it would be what? To get the total charge, I do the equivalent capacitance times the voltage. Which would be 20 microfarads times 50 volts. What you got there? Q total of 1,000 microcoulombs, which we will not write as 1,000 microcoulombs, right? What will we write that as? What is 1,000 micro? A milli, right. This is 1 millicoulombs. All right. 1 millicoulomb. And although we'll be back to the microcoulombs here in a second. So my question then is, what's the charge on each? Well, symmetry, right? Says that there is Q equal to 500 microcoulombs on each capacitor, right? Because the sum of the charge on both has to be equal to 1,000. So that means it has to be 500 microcoulombs on each. All right? What if it wasn't so nice, though? What if instead of having, 10 and 10, let me do example 3 over here. So let me mess up our symmetry. So we'll stick with the 50 volts, but this time we're going to do 40 picofarads. And over here we'll do 10 picofarads. All right? So I could say there's ground down here, and up here you've got V equals to 50 volts. That's another way of saying that I have 50 volts between the terminals, because that is by definition where 0 volts happens for us, okay? Okay, great. So then this is the same as a 50 picofarad, right? Capacitor, that's the equivalent capacitance. And so my Q total is what? I got my 50 picofarads times my 50 volts. That gives me 250, or 2,500? 2,500 picofarads. Or if you prefer, we could say 2.5 nanofarads, right? Because a pico is 10 to the minus 12. N is 10 to the minus 9. So 2,500 is 2.5 nanofarads there. What's that? Oh, coulombs. Ooh, man. I should just stop. What other damage am I doing to you guys today? I'm glad you guys are stopping me. Thank you. Did I just ruin my day? If I found out about that after class, I would just totally ruin my day. Thank you. You saved it. That's good. Okay, so we know that this is equal to the charge on the 40, right? Plus the charge on the 10. But what else do we know? Well, we know that 50 volts is equal to, what's it equal to? Well, 50 volts is equal to Q40 divided by 40 picofarads. And it's also equal to Q10 divided by 10 picofarads, right? So I can work those out. Now I've got two equations, two unknowns, right? My two unknowns are Q40 and Q10, and my two equations are what I wrote right there. So let's see here, like, I guess we'll solve, I'm gonna plug that one into here, and I don't know, what do you guys wanna do? We can, let me solve this bottom one for Q40. Which gives us 4Q10, right? because 40 picofarads over 10 picofarads is just 4. So I get Q40 is 4 times Q10, which then when I put that up in here, it gives me back 2.5 nanocoulombs is equal to apparently 5 times Q10, right? So Q10 is, I guess, 0.5 nanocoulombs. And Q40 would be what? 2.0 nanocoulombs. Let's take a moment to appreciate what's going on. Let's talk through this. How's this going? The larger capacitor, right, has what? The larger charge. Isn't that right? The smaller capacitor has the smaller charge, right? And that has to happen because they're both, the ratio of the charge to the capacitance has to be fixed at the common voltage to both. So this makes sense. Right. Any questions? All right, so the key to solving these kinds of problems is to remember two things. For a parallel, same voltage across both, and the sum of the charge you can figure out from the equivalent capacitance. All right? And then the charge on the individual elements, it all has to go back to the definition of C equals Q over V. You just put those things together. For the series one, you know that the charge is the same for each, and you know that the sum of the voltage drops has to be the net voltage drop. And so that's how you work these two kinds of problems. Now you can also have problems which are an amalgam of both of these ideas, right? There are problems which involve a middle ground where instead of talking about a series or a parallel, we're talking about some kind of combination of those two ideas, right? So I won't do this, I'm not going to do this circuit analysis kind of stuff for the other one, but I will show you how to find the equivalent capacitance for a few more examples, because I think you need to see that. Although I think some of you guys probably already know this, if I had to guess, but not everybody, right? Or does this get taught in some earlier engineering course I don't know about? Was it already in lab? I sometimes lose track of where we are in lab. Okay, that's not true. It's not sometimes, it's always. Truth in advertising here. I don't know where you guys are in lab. Okay, so example 4. Let us suppose that we have the following situation. We've got 2 capacitors, I'll call it C1 and C2, in parallel like that. And that's in series with a C3 down here. And all of these guys together are in parallel with this C4 over here. I think if we can do this one, we should be able to do a lot of things. So I do it in steps, all right? I say, oh, okay, well this is the same as if I have, you know, like this. All right, so C3 stays the same, and C4 stays the same, and I'm using an equivalent capacitance. I'm using the equivalent capacitance theorem to replace my parallel combination of C1 and C2 with C1 plus C2, right? Because those are in parallel. So this piece right here gives me that. Make sense? I hope. So next up, I deal with the series combination over here. All right, so I'm going to have I've got my C4 over here, right? And I'll put it over here. So my question is, what's the equivalent capacitance of that series combination? Yeah?
C1, obviously C1 plus C2 times C3 over C1 plus C2 plus C3.
So you're telling me 1 over C1 plus C2 plus 1 over C3, all of that to the minus 1 power?
Yes.
Agreed. So sum of the reciprocals reciprocated is the rule for parallel, series capacitors. And then the finishing blow here is easy, right? So this is the same as just one foul total equivalent capacitor with CQ equal to what? C4 plus, 1 over C1 plus C2 plus 1 over C3. And there you go. That's how you do it. Just do it in steps. At each point, replacing either a series or a parallel combination with a series or with the equivalent capacitance. Does this make sense? I hope. All right, good. I want to project some. Now, of course, we can do more of these some other day once you guys have a chance to sit and think about it for a bit. But in the time that remains, I want to talk to you guys about Ohm's law. So, and point of order, we'll come back to capacitors later once we've built up the concept of circuit analysis. And so we return to capacitors and how to charge capacitors in a few lectures. All right, we don't have quite the technology to do that yet because we need to understand Kirchhoff's voltage law and Kirchhoff's current law in order to properly have that discussion. But the one thing we can do with the time remaining is talk about Ohm's law and what is Ohm's law and how's that work. Because this is really, so this would be the analog of like what we did for capacitors last time. What I'm about to tell you is kind of like the underlying physics of resistors. And the truth is that all right, now you guys are going to have to guide me through. What were the steps we did last time? What did you guys told me? I need to, was it F11? And then hamburger. All right, we got it. Okay, F11 hamburger. There we go. Don't go to sleep. Don't fall asleep. Sorry. None of you watch that. That's good.
I've seen that video more times.
Do we? Yeah, it is pretty bad. I don't know, my brother started watching, the cousin started watching it. And like, I don't know. Some of his made up lyrics are just, yeah, I do like that. He's a zombie. That's my favorite one. Anyway, let's see here. Sorry, enough bad lip reading comments. So resistivity basically is a measure of how much material gets in the way of charge flowing. So if you can imagine electrons flowing through the metal and they're bumping into stuff as they're going through, right? The more stuff they bump through. Well, I tried. I love those stupid videos of like messing with like little kids. They get like a a car alarm or whatever, and the kid thinks he's using the force, but it's just the dad, pressing the lights on the car. Like, it's good stuff. Anyway, I'm easily amused. What can I tell you? So imagine this is a wire. You got the flow of electrons this way. Annoyingly, Benjamin Franklin defined charge to be positive in the opposite sense of most charge that flows, which is actually negative charge. So the conventional current is actually opposite of the physical current. I know, it's annoying, but it's true. Anyway, so current, which is charge per time flowing past a wire, you can measure as the current density, which is charge per unit area time times the area, if the current density is constant. Now, generally speaking, you've got to do one of these handy-dandy surface integrals over a surface that cuts the wire to figure out the current as the integral of the current density. Now, we'll come back to that much later in the course. So anyway, long story short, stop that. The current is dq dt, which is the charge passing through a point in the wire at a given time. And you can find a formula for that in terms of the charge of the charge of the charges which are moving. N is the number, I think it's a number density of the charges. A is the area of the wire, and V is the drift speed of the charge that's moving. I don't think I have assigned you a problem about any of this stuff. I'm just telling you a little bit of the underlying theory of physics here, okay, guys? And so the drift speed of free charge, for example, is about 3.5 millimeters per second in copper. So what happens is that when the electric field is applied to the conductor, it generates surface charge which moves the free electrons in the average direction of the opposite the field. And because, like I was telling you, the electrons bump into the lattice of the conductor, energy is lost. And how does that go? Well, voltage is energy times change, electric field times the change in length, right? This is the voltage. We've worked this out, right? For constant electric field, it's like electric field times the length is the voltage drop, right? Like the capacitor. We saw that. And so many times it is meaningful to take the ratio of the voltage dropped to the current flowing, and it turns out that that will be constant. And that constant we call resistance, if there is a constant. Now you might have materials where actually the resistance, quote unquote, is not a constant, but it depends on the voltage and the current, right? It's possible to have materials which are not ohmic, but an ohmic material is one for which V is equal to IR, which is Ohm's law. So Ohm's law says that the voltage dropped is equal to the current times the resistance. Now resistivity is a kind of, in some sense, like a resistance density, kind of, sort of. Specifically, here's how it goes. The resistance is equal to the resistivity times the length of the wire divided by the area of the wire. All right? So the smaller the area, the larger the resistance of the wire. The bigger the area, the lower the resistance, right? So if you've got a big honkin' 10 gauge wire, you know, which is pretty thick, you've got a larger area, cross-sectional area to the wire than you do if you got like a 22 gauge, right? So the resistance is much higher for a higher gauge wire as the system works. And the resistance is also proportional to the length. Now I have some real world, honest to goodness real world numbers to share with you here. Come on, to share with you. Oh yeah, also the resistivity, generally speaking, is a function of temperature. And here I'm talking about light bulbs that get bright when you first turn them on. But this is written in 2010, which is before the advent of the LED, even before the even before the popularization of the, I think the what's it called? Those stupid, yeah, those horrible CFLs. So I'm talking about incandescent light bulbs that are actually, you know, they use a wire that you pass current through to make light, right? Turns out that there is a temperature dependence to the resistivity with temperature. Oh, also, side note, interesting point is that the actual rules that resistance follows, if you were to study the statistical mechanics, in other words, the statistics of how the electrons bump into the lattice of the metal, you'd not find this because it's actually quantum mechanical, the temperature dependence, as it turns out. Anyway, that's a thing you could look at when you take solid state physics here, which of course we don't offer. But sorry, it seems to be a theme. But anyway, so for example, 14 gauge wire has 0.0082 ohms per meter. It works out. And so if you were to say put 2 amps through a 14 gauge wire, and how long did I say? 1 meter. So 1 meter, 14 gauge, 2 amps, you lose 16.2 microvolts, which is, I mean, excuse me, millivolts, not micro. I'm an idiot. You're like, whatever, that's not much. True. If you have 100 meters and you put 10 amps, you lose, what, 8.2 volts. Now we're starting to feel it, right, with a 14 gauge wire. So as a practical, but that's not too bad, really. I mean, I don't know. I think if you're running a power drill or something, that wouldn't be too bad, would it? I don't know. Anyway, here's some common areas for 12, 14, and 22 gauge. And I think that's it for today, guys. I just wanted to share with you Ohm's law today, and we'll start circuit analysis next time. So, well, you're on YouTube now.